Welcome back, Mindsetters. I hope you had a nice little break. You went and did whatever you had to do. You went to the toilet or you went to whatever you had to do. Make sure you got some snacks, some water, something to keep you refreshed so you can pay attention for this next segment because this is our last segment. So make sure you have your pens, pads out, and you're making notes. So I'm going to hand over to Heather. Heather is going to continue the show. Take it away.
Okay, thanks, Ty. Okay, guys, so what E.T. was doing was explaining that second theorem, which is so important. But now that he's done the kind of proof of it, I want to just make sure that you can see that this theorem can actually have a couple of different applications, actually visually. So we need to be able to recognize it. So let's just have a look at what E.T. was saying. Do you recognize that he was saying that when you have an angle hanging to the center, and then that same arc hangs an angle to the circumference, then that one at the center is double the one at the circumference. Okay, now that's the picture that he presented to you. But now if we have a look at these next cases, can you see that once again we've got an angle subtended or hung to the center, but now just a little bit different. Can you see that here the one to the circumference was like directly above it? Okay, so look at this. It's kind of directly above it, and that's how we prove it. If this is 2x, that one's x. But now can you see that here, this one is going off to the side, but the theory is still exactly the same. As long as they're hanging off of the same feet, so in other words, can you see that this piece here, the arc, is subtending to the center, that one is going to the circumference, that one there is automatically going to be double that one there. And whether it's subtended skew to the right or skew to the left, if this one is, let's say, 120, then this guy here would be 60 automatically. And also, here what they tend to do is they tend to be a bit sneaky. They tend to turn the picture upside down. Well, so what? If I had to turn this back again, can you see again that this is the angle subtended to the center, and that one there is the one that they're talking about at the circumference. Now, there's a third case. Can you see that in this particular case, my arc that's doing the subtending is actually the arc of the semicircle. And the angle at the center is 180. It's a straight angle. So we know that this one is actually double that one. And so if that's 180, that one has to be 90, which gives us a lovely body of proof that if you ever have a semicircle, all right, and you have an angle coming off that semicircle, then that one there is going to be 90. And sometimes that's useful in analytical geometry. But of course, it has to be that this one here at the center is 180 degrees. Now, the last one, which is the fourth case, which is the one that's quite difficult to see, is if I've got the arc, the major arc doing the subtending, then this reflex angle here, this one here, not this one here, so this one is 2y, it would be double this guy up here. But this reflex angle is going to be double that one down at the bottom. So if that's a 2y, so let's say that this is 240, then this one here would automatically be 120. And how do we actually substantiate it? We always just say angle at center twice angle at circumference. Okay, moving on to the next actual theorem, which you don't have to know the proof for. The third theorem actually says the following. If you have an angle subtended by an arc, AB, to the circumference, and we subtend a second angle from those same 2 points, all right? Then it says that these two angles are going to be equal to each other. Now, likewise, these two are going to be equal to each other. Now, a lot of candidates refer to this as the bow tie theorem because you can see it obviously looks like a bow tie. All right? Other candidates refer to it as the cat's ears theorem. Okay, but can you see that definitely looks like cat's ears. But if you had to actually write that as a reason in your exam, you'd get it wrong. Okay, that's what it looks like. But the reason for this that we actually give, if we ever use this, is going to be angles in the same segment. All right. Now, I do want to just point out to you two errors that lots of candidates make. My circles are not perfect because they say that you have to be 100% crazy. Do you know that, Ty? 100% crazy to draw 100% circles. Okay.
That I've never come across, but
Okay,
makes
it's
sense.
True.
Yeah.
It's true. Okay, so if I have what I've just been talking about, all right, and if I have this situation, all right, I want you to look at this with interest, all right, very subtle difference. All right, all of these points, A, B, C, and D, are on the circumference edge. Now, this angle here would equal that angle there. This angle here would equal that angle there. And my reason would be angles in same seg. All right. Whereas this one, can you see, although it almost looks like a bow tie and it almost looks like cat's ears, the very, very big difference is that this one is subtended to the center, that one is subtended to the circumference, and so whatever this one is, 2x, that one there is going to be x. And that is an application of angle at center 2 times angle at circumference. Okay. Right, we're now moving on to the next body of theory, which is all about cyclic quads. Okay, now, this is a new word for you, cyclic. All right, cycle, doesn't want to actually take my pen, but let's take cyclic, all right? Cyclic means that you've got a quadrilateral with all 4 corners on the circumference, corners, okay, on the circumference of the same circle. Okay, not different circles, same circle. Okay, now this theorem is actually quite fascinating because it claims that if you've got a cyclic quadrilateral, the opposite angles add up to 180. Right, now I want you to dig deep into your grade 10 syllabus where if you have a special quadrilateral called a parallelogram, all right, what is true about a parallelogram is that the opposite angles are equal. So let's say that's 70 and that's 70, then this would be 110 because of co-interior angles, and this would be 110 because of co-interior angles. So can you see here the opposite angles are equal? Okay, this is something a little bit more special. If you have a cyclic quadrilateral, they are saying that the opposite angles add up to 180. Not that they are equal, but they add up to 180. Okay, so what we're going to do now is we're going to go down and we're going to do that important thing which is called a proof. Okay, so please notice that in a proof, you get given a certain picture with certain elements in the proof. So what we've got is a quadrilateral A, B, C, D. It's drawn with all 4 points on the circumference, and we've got a center at 0, okay, or O. We want to prove that A, let's say, and C add up to 180, or alternatively, ABC, which is this angle, and this angle, we want to prove that those 2 angles add up to 180. Now, do you remember earlier when Ty was proving something, he said that sometimes it's important in order to facilitate a proof that you do a construction. Okay, Now, a construction is something that often gets put into a proof, but never into a rider. Now, Ty went and did a rider afterwards, which is kind of the application of the theory. So what I need to do, sorry, I said Ty.
I was
Didn't
wondering,
I?
like, okay,
Okay, E.T.
itty.
Okay, sorry.
I was like, okay, I
I've
did
been
the
on
rider.
holiday for too long. Okay, all right. So, what you're going to do when you do your construction is you're going to actually join A to O, all right, as we have, and O to C. All right? And when you do a construction, we normally dot it. So we join A to O and O to C. Now, what I would like you to be able to see is that I have now created an angle to the center. So this angle here, all right, I hope that you can all see that, is going to be related to that one up there. Can you see that AOC is going to, let's say, be 2x, and ADC is going to be x? Why? Because of that body of theory that we had from previously, theorem 2. So what we are going to do is we are going to say that AOC is double, okay, ADC, and that's because of angle at center twice angle at circumference. And I'm going to chivvy along with this quickly. Then that reflex angle I was talking about, this angle here is 2y. This angle here is y. So the reflex AOC is going to be twice ABC. So reflex AOC is going to be twice ABC. And heaven help you if you ditto in an exam, but I'm allowed to ditto now because I'm running out of time. Now, guys, can you see that what I've got at that central angle here, all right, is a 2x and a 2y. But what do I know about the 2x and the 2y? Can you see that that's a whole revolution? So what do we know about 2x and 2y? We definitely know that that comes to 360 because it's a revolution. Okay? And finally, we can therefore say that 2x plus y comes to 360 just by taking out my common factor. And so that means that my x and my y come to 180. So therefore, I've proved that my opposite angles add up to 180. Okay, I've been a little bit slapdash in that proof, but hopefully I've got the idea through to you that this 2x would be double that one. This 2y would be double that one. That 360 degrees, all right, is going to be angles around a point. And so if those two together add up to 360, then those two add up to 180. Right, this has got huge impact on when we do problems, because the minute that we get something along these lines, okay, and it doesn't matter where my cyclic quad is, all right, if I give you that this is 30 degrees, doesn't look like it, but still, if I give you that that is 30, then I can automatically say that that one down there is 150. If I give you that this is 40, then I can automatically say that that one across is going to be 140. And so if you know your theory in paper 3, it's so wonderful to be able to apply, and these puzzles kind of just fall into place. And you can see that I'm really passionate about this. I really, really love paper 3. Does anybody on the page love paper 3?
Yes, we actually do have a couple of
Oh, we
people. I was
do?
also surprised, yeah.
Oh, good. Oh, good. Okay. So they share my passion.
Yes, they do.
Okay.
Greatly.
All right. So I think, Ty, that I'm done. So if you want to close up the show for us and
All
just
right.
tell them that we're going to do paper 3 again next week.
Okay, awesome. Because actually, we have one of our viewers by the name
Mm-hmm.
of Kashifa. She's always on the show, and I always say hi, Kashifa. She actually says, "Wow, thanks for explaining so much of paper 3 to us. In our school, only 6 students actually do paper 3, and we've never had a teacher explain it to us." And she says, well, the teacher usually just says, you know what, guys, you have to know from here to here in the book by the end of the semester. So for someone to actually help us learn it, help us understand it more is such a help. So she's just saying thank you so much.
It's a
And
great
on
pleasure.
that note, I'm going to say, guys, see you next time. Make sure you stay tuned and keep chatting on the page. But cheers.